Okay, everyone, so we're looking at problem 2 from our study guide. And you're going to notice that the very first thing I'm going to do here, well, is going to read through the questions. That's probably always a good tip. Let's go read through all of these. Kind of feel bad that I never talk about that because I feel like it should be taken for granted that you do that. But it really is important for you to do this. So we got marginal values and expected counts. Write alternative hypotheses and chi-square analysis for the data. State and verify conditions carrying out the inference procedure. Determine the test statistic, degree of freedom, p-value. Make a decision. So we're pretty much going through the entire, all of the steps here of our hypothesis test. The thing I found peculiar about this is we start off with letter A, and letter A asks us for the expected counts. Now, the most efficient way of getting the expected counts would be to use the chi-square GOF, or sorry, the cells program. So we are going to use the cells program before we even do anything else. Well, not quite, because I think we're going to start by looking at the table here. So soft drink. Next one is the gym location. And this is going to be the cafeteria. And then, of course, the total. The first soft drink we have is cola. That's 33 and 57 for a total of 80.90. Next drink is Pepsi. They have Coke and Pepsi in the same vending machine. Texas? Interesting.
Oh, you're getting sick now.
Doctor. 30 and 20. That's 50. Last one is Sprite, a Coca-Cola property. That's 5 and 35. Which goes against everything I've ever seen. Yeah, usually you want the Sprite near the gym.
It's a different location to the side.
Last one is our total column for how many people got soda from the gym. That is 68. And I'm just quickly adding these in my head. So that is 112 for a total of 180, 190?
180.
180. So close. Okay. So that's our marginal values. Remember, your marginal values, it sounds fancy. All marginal values means is the total. And the total's here for this row. That's our margin. I call it margin because it's the far left and the far right. Sorry, the far right and the far bottom. Okay. Before we started, put all those values in our matrix already. So if we take a look at matrix A, for example, yeah, there's all our values. And I'm going to run the cells program just once. Okay. There it is. That gives me a preview about what's going to happen. I get a chi-square statistic, I get a p-value, I get degree of freedom, and I have a notation that I'm supposed to write the probability of the probability that chi-square is greater than 21 is pretty much 0. Yeah.
Did you put in the list in one list you put all the numbers from gym and cafeteria?
No, I put this in the matrix.
You put it in the
Matrix A.
no list at all?
For a chi-square test, you use a matrix. For goodness of fit test, you use a list. Okay, so that gives me that. That's going to be there for me. What I want to look at right now is I want to look at the matrix, the expected matrix. B is unimportant to this problem. So let's look at that expected matrix. I think the easiest way to do that is to go to the edit menu and you get everything in one view.
Oh yeah, that
Yeah, the other way is too much scrolling.
Wait, how do you fill out the expected?
you don't fill it out,
Oh, and it just goes straight to E?
but you have to run this list.
Yeah, Jay.
You want to spec on like all the values, like 18.889?
You know, you can round those. I think 18.9 would be fine. Okay. So what do we have? 34 and 56. I wonder why it does that. That's peculiar. 90. Okay, so that takes care of that first one. Note that those values are not very far away from the the expected count is not very far away from the actual count. So that's not really changing our chi-square test statistic very much. 18.8 and 31.1. Okay, that's a little further away from our expected values. This is what, 11 away. This is also 11 away. Sprite, I think this is where we're gonna see the big difference. 15.1 and 24.9. Thank you. Thank you. So yeah, those values are not that close at all. Okay. So we're looking at Pepsi and Sprite. There seems to be some kind of an association here with Pepsi and Sprite. So that concludes part A. Part B. Alternative and null hypothesis. Sorry. I favor this version of the null hypothesis. There is no association between vending machine location and drink preference. Yeah. And what that means is that there is independence between the two. The kind of drink does not depend on the location that the drink was purchased. Or if I know someone was at the gym, I shouldn't know that they have a higher chance of purchasing, what was it, Coke? Or if I'm told somebody bought Sprite, then I shouldn't be able to make the decision that there's a higher probability they bought it from the cafeteria. Alternatively, okay, an association between vending machine locations and drink preference exists. hypotheses. Okay. And this is the appropriate one you want to use for a chi-square test for independence or test for association. Stop texting. Okay. Questions on B? Good. C. Condition 1 is random and independent. So we are told the sample is random. Okay, we're not told anything about independence, so we will assume the sample is random and independent. Independence is, yeah.
You're asking people about 3 different types of sodas. Can you assume it's independent? Because you're not like, it's 3 different groups, whether it's non-alcoholic, whether it's non-alcoholic.
The independence thing is kind of one of those things where we're still kind of working through. So. The next one, all expected cell counts. So tell me where to look for the expected counts. Okay. You have to have them written down somewhere. You have to tell me where they are. I'm not going to do your work for you. In the parentheses are all above 5. And then, of course, chi-square procedures should be safe. Just getting us set up for the next one, letter D. Test statistic, degree of freedom, and p-value. Again, that came out of the calculator already. It's quit. I should have it in the home screen still. Good. Chi-square is 21.42. Degree of freedom is 2. And see, 0.1, 2, 3, 4, and then a 2, right? I have 4 zeros in a row, so that means that's about 0. Okay. 4 zeros, that's enough to say it's about 0. Letter E. Since the p-value 0 is less than alpha 0.05, we reject the null hypothesis. If the null hypothesis is true, the probability of obtaining a sample is about 0%. Finally, conclude that an association between exists. Okay. Hopefully you're getting the message now, seeing the same conclusion written out dozens of times. Hopefully. Okay. Any questions on 2? Let's move on to problem 3 then. Okay, the distribution of blood types varies from country to country. In 2012, the Japanese Red Cross reported that 30% of Japanese are type O, 40% are type A, 20% are type B, and 10% are type AB. A certain Japanese talent agency publishes blood types of its talent. An entertainment reporter thinks that the distribution of blood types differs from the typical distribution. Assume that means the Red Cross distribution. The reporter gathers a random sample of 51 artists from the art agency's rosters and finds that blah blah 18, 21, 9, and 3. Great. What kind of test should be used? Part A. There is only one variable. With 4 categories, right? The chi-square, goodness of fit is most appropriate. Hmm?
If there's one variable and they don't give us the different proportions for each observation, we assume that it's all the same, right?
Yeah. Yeah. Write a pair of hypotheses that can be used. Null hypothesis. The distribution of blood types at the agency. Sorry. Let pi 1, pi 2, pi 3, and pi 4 represent the proportion of talent at the agency with types. We started with O, right? A, B, and AB respectively. Null hypothesis. Pi 1 is equal to, oh, notice that it says at the agency. Not the entire population of Japanese people. Just at the agency. We're not concerned with everybody. We already know what that is. Pi 1 was 0.4. Pi 2 was 0.2. Pi 3 was point.
Pi 1.3.
Was it 0.3?
I mean, no, pi 1 was 0.3 and pi 2 was 1.5, pi 4 was 0.2 and then pi 3 was 0.2.
Thank you. Pi 1,
It's another one.
0.3. Pi 2 is 0.4. Pi 3 is 0.2. Pi 4 is 0.1. There we go. Alternatively, at least one of the proportions in H naught is incorrect. Part B. Create a table of expected values of the blood types. Well, we might as well make our whole table, right?
Show the conditions for your test.
Yeah, yeah. Let's see, the first one is type O, type A, type B, type AB. Expected? No, observed. So what was this? 18, 21. Tell me if I'm off. 9 and 3. Hypothesized proportion. 0.3, 0.4, 0.2, 0.1. You know, I forgot to put a total column. We should have a total column. Total. So that's 51. That's 1. Expected. Let's see. 0.3 of 51. That's 3 times 5, 15, so 15.3. 4 times 5 is 20, so 20 point, no. That's totally wrong. Yeah, no, that's right. 20.4 to 10.2. 5.1. That's great. Right, so that's our hypothesized and our expected. Next, show the conditions from part A are satisfied. Okay, so we are told the random is sample. Sorry, the sample is random. We will assume this means random and independent. Okay. All expected counts in the table above are greater than 5. Blood type AB just barely squeaked out. Barely.
Wait, it can't be 5, right? It has to be greater than 5.
You shouldn't be put in that position ever.
Huh?
You should never get put in that position. Okay, questions on B. Part C. Yeah.
Can you use this test with proportions?
Well, they're all proportions. We're talking about categorical variables, so everything's a proportion. We use this test when there's only one categorical variable. Part C. Well, we might as well put this in our calculator now. Yikes. 18. Oh, sorry. I should clear off this list, huh? $18, 21, 9, and 3. I forgot. What is this? 15.3? 20.4? 10.2? 5.1?
This is true. I'm just not just like putting it in the table. Let's say you want to like delete one cell. How do you do that?
Oh, delete key.
What is it?
Delete. Clear will work.
Press the clear or something.
Clear doesn't work?
No.
5.1. Okay, just get to the home screen. And we're going to run that program. It's the Goff program. My observed are in L1. My expected are in L2. Thank you very much.
What does golf stand for again?
Goodness of fit.
If you put just golf, you get Delta Rapid put on
You should put Goff. You can put Goff. 1.53. Okay, so chi-square is 1.3. Thank you for changing this to the what's the next one? Degree of freedom equals 3. And the p-value is equal to the probability that chi-square is greater than 1.5. I don't know why I put 1.4. That was like 60, 68, 23. Is that everything? No? Okay, so what are we writing down? Since the p-value is 0.6823 is greater than alpha 0.05, we fail to reject the null hypothesis. If the null hypothesis is true, we have a 68% chance of obtaining our sample. Since this is likely, we have no evidence, or we cannot conclude that the blood type proportions from the talent agency differs from the Japanese Red Cross proportions. That's kind of it. Okay. Any questions before we wrap it up?
Can you do number 7, or are you gonna do that?
I'll do it. We have time to do 7 probably.
I don't understand what it's asking.
Okay, so we have all of these chi-square statistics, right? And we want to figure out the p-value that's associated with them. So the p-value is equal to the probability that chi-square. Let's do the first one. The probability that chi-square is greater than 3.84. Okay. How many degrees of freedom do we have? I think it was 2, right? Okay. So basically, let's calculate that. 3.84. So we're going to go to the distribution menu. Chi-square CDF 3.84 with 2 degrees of freedom. 0.1466. Let's do it again. This time we're going to do it for 5.99. Okay, 0.500. P-value equals Now we're going to do it again for 7.81. Seven point 81. 0201.
Next one is 0087.
Thank you. At 9.49. 0407.
0087.
So,
And then the last one is 8.8 times 10 to the negative 4. So you could say approximately.
14.7. Okay, so which is the first one that would be rejected? What's the smallest one that would be a reject? Yeah, this is the smallest chi-square that would be rejected. So, yeah. You know, obviously you would reject for these three p-values right here. But what is the smallest chi-square that would get rejected? 7.81 is the smallest chi-square that would be rejected.
The 5.9 we wouldn't reject.
Yeah, we wouldn't reject that. Because it's actually above, yeah, it's above 0.5 actually. Yeah. In fact, next year I need to change that so it's less vague. Okay.